All right. Well, we finished everything for the exam, I believe. Let me just double check that. Because we're only doing up through capacitor circuits. We're not only through chapter 2. I'm sorry, what? Oh, not talking to me. All right. Yeah, so we finished all the way up through what we're going to be doing for the exam. That's going to be chapter 1.5. That's the chapter on Gauss's law. And so that'll be similar to what we've seen before with, fluxes and fields, except now instead of doing gravitational fields, we'll have electric fields. So you'll see some similar questions. Listen, with these exams, you really need to make sure that you go through the homework, because sometimes I just go through the homework and I pull questions almost verbatim through the homework. You're going to have 15-ish multiple choice questions, and then you have 4 to 6 free response. There's no take home on this one. I know that I said I might give you a take home, but I just wasn't able to come up with a good derivation for the potential that's significantly different from anything that we did. So I decided to do no take home on this. I'm sorry for that if you were looking forward to it. So 4 to 6 free response. It'll be worth 100 points, covering chapters 1.5 and 2. Now let's look at the particular topics that we'll have. I'm going to sort of go through the notes, but I'll keep a running list on the other side. Let me start a new thing here. Oh, can I have both of these open? And then if you have particular questions, we can go back and revisit some of those questions. But in short, you'll see Gauss's law. I'll give you some regularly shaped object, kind of like the cube that we did, and you have to figure out the total flux that's going into that object, and then from that total flux, you'll have to find the charge using Gauss's law. Gauss's law is on your equation sheet, but you need to know how to calculate the flux. Pull up our notes here. All right, so on chapter 1.5, you need to be able to calculate the flux for a 3D object. And then once you find that flux, calculate the charge enclosed. It'll probably be like a rectangular prism. But I haven't written a test yet, so make sure you understand this whole bit about the dot product. We had some similar multiple choice questions. Remember where I talked about the flux, how the flux was going at different angles, and how does it affect the flux? Because you only get a component of the field lines that are actually due to the flux. You follow what I'm saying? Remember that multiple choice question we had last time, where I had the surface area and then the field lines went out at an angle? So make sure you understand that when it's at an angle that your flux is reduced because of that dot product. See, these are just calculating the flux due to these various shapes. And then Gauss's law. You could see something like this where you just have, I tell you the amount of flux or the amount of charge enclosed, and you just have to calculate what is one or the other. Just applying Gauss's law. But you'll also likely have one similar to this one, this example, where we calculated the total flux for all 8 sides of the cube, all 6 sides of the cube, and then determine the charge enclosed. I think that's about it for chapter 1.5. Let's see. You will not have to derive Coulomb's law. So no Coulomb's law for this. No derivations at all, in fact, on this test, and no take-homes, as I said. All right, work through the homework. The homework will sort of guide you into what I expect you to know. Yeah, look at that homework. It'll be a good indicator of what you'll see on the test. All right, and then in chapter 2, this is sort of the big chapter, so we'll have potential energy, capacitance, and capacitor circuits on this. So in chapter 2, We'll have potential, potential energy, capacitors, and capacitor circuits. Related to the potential energy, we also have work. Those are very similar. If I do work assembling a group of charges, that's equal to its potential energy. Also regarding potential, you need to know how to find the potential due to a point charge. You need to be able to know how to find the electric field given a function for the potential. That is, this whole E is equal to negative del V del X in the I direction, or EX rather. We did that where we did the partial derivative, sometimes called the gradient, if you get that in Calc 3. Need to know how to do this sort of thing, where if I have an object that travels through a certain potential, be able to calculate its speed. So that sort of falls into this category with work, that work is equal to my change in kinetic energy. Let's see, this is on page, what page number is this? 57 of your notes, page 57, something similar to that. It becomes pretty important later when we get into mass spectrometers. Potential difference, need to understand these potential functions. That's like when I have V versus X, and I can create wells in the potential function to isolate either positive or negatively charged particles. We had some questions about this. Quick test. As I say, you need to know how to find the potential due to point charges, and then also know what amount of work is required to move a charge into the potential due to another set of point charges. So for example, let me get another page here. If I have charges here and here, then you can find the potential at a point up here. The potential is equal to KQ over R plus KQ over R. Right, where this is Q, and this is the distance R here and here. Remember, they add like scalar quantities, so I don't worry about the any signs for the direction, but I do include the signs for the charge. So remember, whenever we're dealing with scalar quantities, that is V and the potential energy, you include the signs for the charge. Because you can have negative potentials. You don't have negative electric fields, right? Because you give the direction, but you can have a negative potential. Now, if I want to determine the work required to move a charge, so let's say that I have a charge over here, and I want to know what work is required to move it into that position, that work required is equal to Q delta V. We did some problems like that. But then also, when I get three charges, two or three charges, say Q, Q, and Q. We did this for masses as well back in chapter 0, but I want to know how to find the potential energy due to these three charges. And I want you to remember that you have three potential energies. You have this potential energy, you have this potential energy, and you have this potential energy, and then the sum of the potential energies is the sum of those three. We did a couple problems like that in class, and it's very similar to what we saw for masses in chapter 0 when we were doing the gravitational potential energy due to Newton's law, Newton's universal law of gravitation. All right. Let's go back to our little summary up here. That's like here on page 59. There's our collection of point charges. determining the potential. You are not going to have to do this. So this is on page 62, but you will not have to do this. You will not have to do any derivations at all. This has to do with our potential, like the potential of the 2 or 3 charges. You won't have more than 3 charges because it just gets sort of burdensome to calculate. I might give you a configuration of charges and ask you to draw the equal potential lines. So what I would give you, this would be just worth probably a few points, 3 to 5 points, is I'd give you, a positive charge and a negative charge, and I'd already have the field lines drawn, and all you'd have to do is come along and draw the equal potential lines, being careful that the equal potential lines are at 90 degrees to the field line. So it looks something like that. But I might give you a more complicated system of charges, right, maybe 3 charges, and then ask you to draw the equal potential lines. But the key here is that you always look to make sure that my field lines are 90 degrees to my equal potential lines. Right. It won't be terribly difficult, but it might be more complicated than this. All right? And then I think we get into capacitors. Oh, and then also you need to know how to find the electric field given a potential function. This is immensely useful because it's kind of hard to find the electric field, but it's pretty easy to create a potential that follows a certain function. And then once you know the potential, you can back out what the electric field is. It's a lot easier mathematically, and it's just, as far as measurements, it's easier. So I want you to be able to, given a potential function, take the partial derivative of the x, y, and z components of that potential function and find the electric field at a particular point. It'll be like very similar to the example that we did in class, where I just give you a function, and then you find ex, y, and z, and then I'll give you some coordinates, and you can plug in the x, y, and z coordinates for that. We did an example in class like that. There's one like that in the homework. There's practically one on every exam that I've ever given. So if you need extra practice with that, by all means, very likely to see that. There's another example. Okay, and then we have capacitance. Now with capacitance, you'll see a couple of things. You'll see Q equals CV, finding the charge on a capacitor, just sort of basic stuff about capacitors. It has to do with the epsilon naught A over D. Actually, we have a kappa in here as well. That's our dielectric constant. So know the different relationships for capacitance. For example, if I increase the area of the plates, that increases the capacitance. If I increase the separation, that decreases the capacitance. Those equations are in your equation sheet, but make sure that you're able to follow them. We have, on our concept test questions too, we had several questions related to that. I haven't posted those yet, and I apologize, but I will this morning as soon as I get back to my office. But if you are here, you have the answers. Okay? I'll probably give you, I might give you, I mean, we have a lot of material, so some of this isn't going to make it on the exam, but I'll probably give you a capacitor and give you its dimensions and its dielectric constant, and you just have to find the capacitance. And then I might ask you, well, how much charge does this hold if it's attached to a battery of a certain voltage? And then you can use this, or the Ohm's law of capacitors, to find that charge. Then with circuits, you'll probably see, you'll certainly see a circuit that is akin to one of the more complicated circuits that we did. So where is it? All right, one something like this. So you'll very likely see one something like this. You might also see a simpler combination circuit. Maybe a circuit that just has 3 or 4 capacitors that are in series or parallel, something like this, that's hooked up to a battery. So you can see both of those, or you could just see the more complex circuit. Okay? It depends sort of how much material we have from the other stuff. There's quite a bit of stuff for this test, so probably it'll just be the more difficult, or the one with more capacitors in it. And as you know, the difficult part with that is not so much finding the charge and the voltage. The difficult part is getting this circuit into this circuit and recognizing that these two are the same. And then if you know the rules about finding the charges and the voltages, the rules how they apply to all the capacitors, then that sort of falls out. I mean, it's not easy, right? But with practice that comes. But the difficult part I find for me is getting from here to here. That comes with practice. So look back at the old tests. Every test has a capacitor problem, and they're all slightly different, either different values, slightly different configurations, but they're also all very similar. So that'll afford you very good practice. And there's a homework problem too, at least one, maybe two homework problems. So you'll have one of those as well. I think the last thing that we did was energy of capacitors. And it'll probably just be tacked onto a question. Like if you have a capacitor, I say, oh, if you have this voltage, what energy does that hold? And you'll see that form sort of in the old test. You need to be able to find the equivalent capacitance, be able to find the charge and the voltage on every capacitor. That's it for the test. Fluxes, Gauss's law, potentials, potential energy, and capacitors, including circuits and capacitors just sort of by themselves. How y'all feel about that? This is a difficult test, right? I don't want to scare you, but it is sort of one of the more difficult tests. I think exams 3 and 4 get a little easier, but this is probably one of the more difficult tests. Exams 1 and 2 are sort of the more difficult because we're dealing with more abstract ideas and looking at fields and potentials. All right. Which of these areas do you feel is your weakest, or what do you want to go back and revisit some of these things? Do you want to revisit maybe the capacitor circuit, or the potential, or the electric field from the potential function, Gauss's law, fluxes? All right, let's look back at some old tests. Now, unfortunately, with the fluxes, I don't have a whole lot of old exams for these because we've only been doing fluxes and Gauss's law for a few years. Let's see what we got. Okay, so you'll probably see something similar to this. And this is very similar to the example that we worked in class, but you know, that's what you'll have. And so remember with fluxes, if we want to find our flux, where are we? We find our flux so that we can find the enclosed charge. And when we're finding our flux, it's going to be the integral of E dot dA. Now, we're not actually doing integration per se, but we are doing integration because we're summing up all the individual parts. And that's really what an integral is, that we're just summing up the individual parts. So as it applies to something like this, download this. You want to take the dot product of E and the area vector for each of them. So our flux is equal to the integral of E dot dA. And notice that our area vectors, so first of all, I have 6 faces of this cube. I'm looking for those faces where the electric field is in the same direction as the area vector. So for example, here my area vector points in that direction. Over here it's in this direction. Over here it's in this direction. And down on the bottom face it is in this direction. And then we have the front and the back faces. The electric field comes out of the front face, and on the back face it goes into the page. Now, some of your faces won't have a flux because the field lines just won't go through those faces, and so I won't have anything that is parallel with the area vector. So you want to look at our electric field. Here I have a component of the electric field that's in the I direction. So this electric field will interact with this area vector in our dot product, right? Because I dot I is equal to 1, I dot j is equal to 0, I dot k is equal to 0. This component of my electric field will interact with this and these components of my area vectors and give me a non-zero flux. However, which of these faces, the top, the sides, or the front and back, will have no electric field at all, or have no electric flux at all? The front and the back, because the front and the back area vectors are in the z direction, or the k direction, out of the page and into the page. And notice that the electric field has no k. So I'm just not going to worry about the front or back. All right, so let's do the top. E dot dA is equal to, well, E on the top is going to be 3y. I'm just including that. I'm just leaving off the I because I know that I dot j is going to equal to 0 because my area vector is in the j direction. So I'm just going to leave off this part of my electric field. If you want to write it out, that's okay, but I'm going to leave it off here. And so that gives me the area here is 3 times 3. So it's going to be, the area vector will be 9, has a magnitude of 9. And so that gives me 27y. That is the flux for the top. And the value for y is equal to 27 times 3. And so that's 81. What's it? Newton meter squared per coulomb. All right, so that's my flux for the top. And then I do a similar thing for the bottom. But you can probably see, or some of you might see, that the bottom is going to go to 0. Why does the bottom go to 0? The bottom face has 0 flux through it. Why is that? The question is, what is the magnitude of the electric field in the y direction at the bottom? It's 0. And the reason it's 0 is because y is equal to 0. You see how this was dependent upon our y position? Our electric field down here has a magnitude of 0. Our electric field up here has a magnitude that's non-zero. All right, so my bottom face, I'll go ahead and write this out, is E dot dA. That's going to be 3y in the j direction dotted with negative 9 in the j direction. It's negative because this vector points down, but because y equals 0, that's equal to 0. And then we can do similar things for the left and right. I'm going to do the right first. E dot dA is going to be 2i. I'm leaving off the 3yj term because j dot I will equal to 0. You know, I'll go ahead and write it out just so you'll see. 3yj dotted with my area vector, which is on the right face, which is this face right here, is going to be 9i. And then when I dot this, I get 18 Newton meter squared per coulomb. So that's the right face. And then the left face, well, it's going to be identical, except for it's going to be negative. So the flux for the left face is E dot dA, 2i plus 3yj, dotted with negative 9i. Just take a little step back here. So I always start with this, E dot dA. That is my definition of flux. And I'm doing it for every individual part because I want to do the sum of all the fluxes. Because I'm doing the integral. That's sort of the poor man's integral. And so here's my flux, or excuse me, my field function that's given in the problem. And then this is my area. This is just the area of the face, you know, side times side gives you the area. But then you also have to consider the direction. The area vector will always be perpendicular to the surface and pointed outward. And so for the left face, that's why I have negative and 9, because it's a 3 by 3 by 3 cube. Right? If it's a rectangular prism, you have to figure out the area of each individual face. But in this case, all the faces have the same area. Then I do the dot product, recognizing that I dot I is equal to 1 and J dot I is equal to 0. And so that gives me, in this case, minus 18 Newton meters squared per coulomb. And then if I want to know the total flux, I have 81, I have 18, and I have 18. The total flux is the sum of those, so it's going to be 81 Newton meters squared per coulomb. Very, very likely that you'll have something like this. That was really the only big thing that we did in chapter 1.5. So you're going to have a problem similar to this. Nicole?
What's an example that you did? Just wondering, like, for this particular problem, you didn't give, like, that x is 1 and x is 3.
Mm-hmm.
How do you know that number? Like, how do you know?
Oh, I drew it up. It wasn't in your workbook, but I don't know, I just didn't put the figure in there.
Okay.
But you will have to figure it. It'll be like this.
Okay.
It'll probably be a cube or a rectangular prism. Yeah, we haven't really done any curved surfaces. I mean, you could probably figure it out, but yeah, we'll just stick with simpler figures. And you just have to figure out the area, right, of the cylinder. You don't want to do that, but we'll stick with simpler, you know, just more little. Is that a word? Trapezoidal? Like this. Cubes are prism, or rectangular prisms. Did I answer your question, Nicole? Nicole? Maybe. Oh, well, think about it. Let me know if you have. You're going to have to do one of these, so make sure that you're prepared for it. And then once you find the total flux, if you want to know the charge enclosed within the cube, then you go back to your Gauss's law. So our flux is equal to our enclosed charge divided by that epsilon naught. That's a constant. It's given on your equation sheet, and so we would just take this and solve for Q, which is our flux times epsilon naught. It has a value of like 8.85 times 10 to the minus 12, but it's on your equation sheet. And the Gauss's law is also on your equation sheet. Okay? We've done similar things to this. We did similar stuff on the last exam, but you're going to do it again on this exam. May or may not see this stuff again. I don't think you do this in PChem, but if you go to graduate school, you'll probably see stuff like this. Because, you know, charges are pretty important, to chemists especially, but if you go into electrical engineering or anything, if you take an upper level electrodynamics class, you'll certainly see this. Alrighty? And it's fun, right? I mean, fields are kind of cool, especially when you're doing these integrals and the dot products are all coming back together and the 3D shapes and stuff in your head. Okay. Any other questions about this? Probably going to see your electric field due to a potential function. That was the partial derivative that we did. Again, you'll probably also see the potential due to point charges. May or may not see potential energy due to point charges. Not sure. Other questions? Or particular areas that you want to look at? You're going to take the exam now? We could just give it. I give you till 9:30. You want it? You want your exam now? No. What's that? You just be done with it. And then you have the weekend free. You know what?
Be done with physics too.
No, we have 2 more exams. No, I don't think I'm in the class. All together. That's a crew. Okay. Well,
How many people? Kind of do like each person, each 20 people do the test.
our sharp group is students who can do offensive things. Okay. Any other questions? What, Dustin? All right. Well, anything else? Circuits or circuits? Central, energy, electric fields. Dustin?
Just do a capacitor circuit.
Yeah, I think that would be good because I think that's sort of one of the weakest points. Thank you for asking. I was going to do it anyway. What's that? Right. Again, my recommendation to you is that you go back and you look at all the old tests, and all the old tests have these on them. So let's just go back. I don't know. We'll just do this one. I think this one. Yeah, this one has it. This is the spring 14. Okay. Well, this is a funky one. It's a little bit different than what we've seen before. But with the resistor circuit or capacitor circuits, when you come to them, you want to always start on the big side of the battery. I don't know. You can start on the small side of the battery, but I just always start on the big side of the battery. So when I come to a circuit, I know, okay, well, this is where I start, and this is what I do. And I recommend the same for you, because you come to this, and you're like, oh, what the heck do I do with this? All right. But when you just sort of have a starting point, and then you start redrawing the circuit, then I find that it sort of fits into place for me. So I'm going to start on the big side of the circuit, going in this direction, on the big side of the battery, so I'll redraw it. I come to my first junction right here and recognize that it splits into two junctions. Okay, so I have two junctions there. And then on this one, I have two capacitors. I'll do this on the bottom. I have a 4 and a 4 microfarad capacitor, there and there. Up here on this one, I have a 6 microfarad. And then notice that I break up into another junction. Now let's go back to the bottom branch, because when I come here, you come to this point and you say, gosh, what do I do here? But when you come to a point like this, if you have a clear path back to the battery, notice I have a clear path with no elements at all back to the battery, you take it, because that's what the electrons are going to do. They're going to take that path directly back to the battery, and you can just effectively think of this being the closing point of that branch, that it's going to go directly back to the battery. However, when I come to this junction, I don't have a clear path. It actually splits 2 more times. I get a 1 and a 2 microfarad capacitor. And then those close off, and then these all go back to the battery. So this is 12 volts. So that is my circuit. It's the same circuit. These two are identical. It looks funky because I got this whole little thing right here, but these are identical circuits. Okay, now from this, you might be able to just look at this, and like you might be able to say, well, gosh, this is a 6 and a 3 right here, and this is a 4 and a 4. A 6 and a 3, that's 2, right? 6 and 3 microfarads in series is 2 microfarads. And then a 4 and a 4, that's a 1 over a quarter plus a quarter. That's also equal to 2. So 2 and 2. And so my equivalent then is equal to 4, because 2 plus 2 equals 4. But I like to redraw my capacitor circuits. It's a good practice. You'll like it. It'll help you with the resistor circuits we'll do next semester, or next chapter. This is 2. This is 2. Actually, I'm going to do another. This is 6 and 3. Two and 2. And then the 2 and 2 give me 4. All right, so my equivalent is 4 microfarads. I have 12 volts here. That means on this 2 microfarad, I have 12 volts and 12 volts. I know that's true because these are in parallel, so they have the same voltage, 12 and 12. So I also have 12 here. And here at the top, I know that 6 and 3 are going to split up that voltage. And you might be able to just look at it and tell me what that voltage is, because we've seen this combination before. You might just remember it or think about how the capacitors split that up. Remember, small capacitors have big voltages. The sums of the voltages have to add up to equal the total. So this plus this has to equal to 12. And one of them has to have twice the voltage of the other. Small capacitors have big voltages. The sum has to add up, and the voltage will be proportional to the capacitors. So that means I'm going to have 8 volts and 4 volts on these two. 8 volts and 4 volts. Or you could say I have 24 microcoulombs. That's Q is equal to C times V. And then here, 24 microcoulombs, 24 microcoulombs. So 24 divided by 6 is 4. 24 divided by 3 is 8. Almost done. If I have 4 volts here, I have 8 volts here and 8 volts here. I have 12 volts here. So these two are identical capacitors. They split that up. They're identical, so they have the same voltage, but it's split up. And then I'll just go through. I have all the voltages for every capacitor, and I can fill in my chart here. So let's see. C1 is the 4 microfarad capacitor. And C2 is also, so these are 6 volts, 6 volts. These two capacitors are these two. And then V3 is our 6 microfarad, that's 4 volts. V4 is the 1 microfarad, 8 volts, 8 volts. And then once we get that, I can go through and calculate my charge. Q is equal to C times V. That's 6 times 4, 24 microcoulombs. 6 times 4, 24 microcoulombs. They should have the same charge, right, because they are in series. Capacitors in series have the same charge. Q3 is C3V3. 6 times 4 is 24 microcoulombs. C4 is 1 microfarad, so this is 8 microcoulombs. And C5 is 2 microfarads, so that's 16 microcoulombs. And then that's it. I might also have a question where I just ask you, what is the energy stored in capacitor number 3 or whatever? You do that 1/2 CV squared. That equation is on your equation sheet, so don't bother memorizing it, but it's there. It'll be something similar to this. So look back at the circuits. I know you probably look at me working through it and it's like, oh, yeah, of course. Or maybe you look at it and say, oh, I don't really know how to do that. But really the way that you'll tell if you know how to do it is sitting down with a blank circuit in front of you and working through it. And on the old test, there are lots of examples. In the homework, there's an example. You can take, some of the ones that we did in class and just sort of rework those. Jesse?
What's up with the 6 microcoulombs and 4 volts with 3 volt? You said, I thought you said that the big capacitor has that.
Did I say that? The smaller capacitor has the bigger voltage. It's different for resistors. And fortunately, we don't have resistors on this test. But the smaller capacitor has the bigger voltage. We can see this because, think about it, I have 24 microcoulombs on this capacitor. So these two, because they're in series, capacitors in series have the same charge. I have 24 microcoulombs, 24 microcoulombs. So if you don't know how these voltages split up, you can think about their charges and then get back to their voltages. Each has 24. Divide the charge by the capacitance, and you'll get the voltage. Does that answer your question? Sorry if I said that. That wasn't correct. You need to practice your circuits, okay? This weekend. I know you have other things going on, but practice these circuits because you will see one. Definitely going to see a circuit. Definitely going to see the flux of the charge, Gauss's law. And then we'll have a couple other potential, other things. 4 to 6 questions. Anything else? Practice. All right. I'll see you on Monday. We'll be in this room at 7:15, okay? 7:15. So there'll be a seating chart on the door, just like always. Come on, have a great weekend. I'm not going to be around this afternoon, but I'm around for a couple hours this morning. But if you have questions over the weekend, I'll be back Saturday evening, so you can shoot me an email, and I can answer them over email or over the phone too.